VSEPR theory. What do we use VSEPR theory for? What is its point? VSEPR theory is a means by which we represent molecular geometries with compounds that we're looking at. This applies to molecular substances rather than ionic substances because molecular substances have discrete bonds. Now, VSEPR is an acronym which stands for Valence Shell Electron Pair Repulsion. This acronym gives us a very good indication of how the theory operates. Looking at the word valence and the word shell. Valence shell is the outermost electrons in an atom. These electrons are paired, so electron pair, either a bonding pair or a non-bonding pair. And then the word repulsion because electrons repel each other since they are both negative particles. So VSEPR theory operates upon the repulsion that occurs between pairs of electrons in the outer shell of atoms that are bonded together. These electrons will try to gain the biggest distance separation that they can, and in doing so will move away from each other and establish the overall molecular geometry. So if I consider a 360-degree circle, I can break this down and establish a geometry between atoms along this circle. There must be at least 3 atoms in the molecule for VSEPR theory to apply. If there are only 2, the molecule will always be a straight line, and there is no need to apply a greater theory to understand its geometry. Looking at the molecule, we look at the angle of the outer atoms versus the central atom. In order to have an angle, I must have 3 points, and if I consider the relation of the 2 outer points to the central point that connects them both together, then I can see what the angle distance is between the 2 outer points based upon the angle that they form. The electron densities that we consider are always pairs. They're either bonding pairs or lone pairs. And it doesn't matter whether or not the bonding pairs are double bonds, single bonds, triple bonds. If I have 2 atoms connected together by a bonding pair, I consider them to be equivalent whether it is single, double, or triple. Lone pairs are considered to be a single electron density for only the 2 lone pairs. So if I have 3 lone pairs on an atom, then that's 3 different densities. If I have a double bond, that's only 1 density. Only the electrons on the central atom and the bonds between atoms are important for VSEPR theory, since the terminal atoms' electron lone pairs do not make a difference. So what system do we use to look at this? First, we have to identify the central atom of the molecule. After that, we count the number of atoms that are bonded to the central atom, the number of lone pairs that exist on the central atom, and from this we can establish geometry. There are 2 different types of geometries that we deal with. There are molecular geometries, which are the actual geometry we can look at because we can't see electrons through spectroscopy usually. And then there are electronic geometries. Molecular geometries look at the configuration of the atoms. Electronic geometries look at the configuration of the electron density regions. So looking at several basic configurations of these molecular geometries, if I look at the formulas for CO2, NO3-, NH3, and CH4, I find the central atom, and these respectively are C, N, and C. The total number of atoms in each molecule are 3 for CO2, 4 for NO3, 4 for NH3, and 5 for CH4. CO2, NO3, and CH4 all have no lone pairs on their central atom. NH3 has a single lone pair. So the total number of electron density regions in each of these molecules is 2 for carbon dioxide, 3 for the nitrate ion, 4 for ammonia, and 4 for the CH4 methane molecule. So looking at these Lewis structures for the respective molecules then, CO2 has a Lewis structure with 2 double bonds between the oxygens and the carbon. NO3 has single bonds to 2 oxygens and a double bond to the 3rd oxygen. NH3 has 3 single bonds to hydrogens and a lone pair. And CH4 has 4 single bonds to different hydrogens. So we can see where the electron density regions are. There are 2 on the carbon for CO2, 3 on the nitrogen for NO3, 4 on the ammonia, and 4 on the methane. So looking at electron geometries are based on these numbers of electron density regions. The lone pair is a single electron density region, and a bonding pair or pairs is an electron density region as well. The central atom determines the overall geometry. Now there are 3 standard electronic geometries and 2 electron geometries that arise from exceptions to the octet rule. The standard electron geometries, and if we look at the way that I draw out VSEPR theory, it's a 3-dimensional structure. So I use 3 different conventions of lines to represent the atomic configuration. A straight line, just a single straight line, is considered to be in plane. A solid wedge is considered to be out of plane, sticking out of the computer towards you. A dashed line is considered to be into plane, which is sticking away from you into the computer monitor. So if I have only 2 densities, I have a linear structure that has a 180-degree difference between the 2 atoms. 3 densities gives me a trigonal planar. If you look at the points, connect 3 points together, I wind up getting a triangle between the 3 points and then the central point in the middle. It forms a 120-degree angle between 2 points on the outer edge. If I have 4 densities, I have what's called tetrahedral. Tetrahedral has a 109.5-degree difference, and it's something like having a tripod with a camera stuck on top with these 4 different points, with the center of the tripod being where the central atom is. Octet exceptions bring 2 more electron geometries to the table. We have 5 densities, which is called trigonal bipyramidal. This is kind of like combining a trigonal planar and then running a single straight line through the middle of the central atom, going perpendicular to the rest of the atoms. There are 3 different angle geometries in this. There's a 90-degree angle between the points that form something of a T shape on the right-hand side. There's 180 degrees between the top and bottom atom, and 120 degrees between each of the atoms in the central planar area. And then if I have 6 areas of electron density, I form an octahedral. Octahedral has a 180-degree angle between atoms that are opposite each other, and 90-degree angles between all other atoms in the molecule. So looking at molecular geometries are based upon electronic geometries, but we have to name them differently if not all of the electron regions are bonding regions. So looking at a standard compound with atoms A and B, and then U representing unshared pairs. So A is the central atom, B is the number of bonded atoms, U is the number of unshared pairs, and the overall repulsion between the bonded atoms and the unshared pairs is that 2 unshared pairs repel each other more than any other pairing. An unshared pair and a bonding pair repel medium, and 2 bonding pairs repel the least, because of the presence of the 2 nuclei holding the electrons more in place. So molecular geometries then are based upon angles between the atoms rather than the number of electron densities. They only consider atoms in the molecule and are not always the same as their electronic geometries from which they arise. For example, if I have a central atom with 2 bonded atoms and 2 unshared pairs, it has a total of 4 areas of electron density, which would be tetrahedral and electronic, but it forms an angular molecular geometry. So looking at the different standard geometries that we have, not including the octet exceptions, which would be something we discuss in a different setting, we have the linear electronic geometry, which has a molecular geometry of AB2. If I remove one of those bonding pairs and make an unshared pair out of the electron density, then I have 2 atoms and I can no longer apply VSEPR theory. So the only geometry that I can get from a linear molecule with 2 bonding regions, or 2 density regions, is a linear molecule. Moving to a trigonal planar electronic geometry, there are 2 types of molecular geometries associated with this. There are the trigonal planar geometry, which is the same as the electronic geometry, and this is when all of the electron densities are bonding. And there is angular, which occurs when one of the electron density regions is an unshared pair. Lastly, for the tetrahedral electronic geometry, we have the tetrahedral molecular geometry if all of the electron densities are bonding regions. The trigonal pyramidal molecular geometry if one of the electron densities is a non-bonding region, and angular if two of the electron densities are non-bonding regions. So looking at the linear electronic geometry and molecular geometry, we have AB2, which is a linear molecular geometry. They are two bonded atoms with no unshared pairs. It forms a 180-degree angle between the two bonded atoms that are bonded to the central atom, and generally is a nonpolar molecule unless those two atoms are of different elements. So looking, for example, beryllium dichloride. This has two chlorines connected to beryllium. They're opposite each other, so they cancel each other in the pull that they have on the beryllium in the middle, leaving it with a nonpolar molecule. Moving on to trigonal planar electronic geometries, I have the AB3, which has got three bonded atoms to the central atom, which is trigonal planar in molecular geometry. There are no unshared pairs in the central atom, and so this forms a 120-degree angle between the bonded atoms. The polarity of this molecule depends upon the arrangement. For instance, with the molecule of formaldehyde, because the oxygen is different in electronegativity than the hydrogens, this is a polar molecule. If I had something that was not different in electronegativity, it would not be a polar molecule. Now, if I take away one of those bonded atoms and have an unshared pair in its place, I wind up with an angular configuration. Angular configuration has two bonded atoms to the central and one unshared pair on the central atom. This forms an angle that is less than 120 degrees between the bonded atoms because the unshared pair pushes them together. These molecules will always be polar. For example, the ozone molecule. Now I represent that lone pair on the central atom with a line as well to show the three different electron density areas, but we wouldn't have a bond between the lone pair and the atom itself. It's just there as a representation, kind of a spatial take-up point. Now for tetrahedral electronic geometries, there are three different molecular geometries associated with the electronic geometry. There is AB4, where I have four bonded atoms, and that is a tetrahedral molecular geometry. There are four bonded atoms with no unshared pairs. This forms 109.5 degree angles between the bonded atoms, and the polarity of the molecule depends upon the arrangement. If all of the atoms are the same, then it's going to be nonpolar. If they are not all the same, it may be polar. For example, the methane molecule, CH4, is a nonpolar molecule because all the hydrogens are the same. Moving on to replacing one electron density area with an unshared pair, we get a trigonal pyramidal. Trigonal pyramidal has three bonded areas and one unshared pair. This forms about a 107 degree angle between the bonded atoms and will always be a polar molecule. The molecule ammonia has that lone pair that sticks up out of the central atom. And so if I look at the actual atoms, it looks like a trigonal pyramid. I've got, if you connect the bottom of the three hydrogens together and then bring them all to the top, it's a three-sided pyramid with a base, which is where the trigonal pyramidal name comes from. If I take away yet another bonded atom, I get an angular configuration, just like I did with the trigonal planar. This has two bonded atoms and two unshared pairs. They form about a 105 degree angle between the bonded atoms because of the repulsion of those lone pairs, and they are almost always polar molecules. Looking at water, for instance, you can see how water has that same tetrahedral electronic geometry, but there is an angular geometry between the two hydrogen and the oxygen.